All right, let's go and get started. Let me see. All right, so first thing, I'm going to go ahead and get the sign-in sheet passed around. So here's, you get that started for me? All right, so real quick, so your homework 3 is due on Monday. I'm happy to find that I think a lot of you have started working on it, which is a good thing. So I've already had a few questions here and there before class. I wanted to open it up for a few minutes if anybody's got any questions about homework 3 in general. Like I've got a few by email and a few a little bit before class. Anybody have any questions on 3? All right. Hopefully you have started it. Remember, it is due on Monday, so hopefully you've at least got a fair amount of it knocked out. Don't forget, we're having our first celebration of learning, our first exam next Friday. The homework will be due on Monday. We will have our exam review on Wednesday. So on Wednesday, make sure you're coming prepared to ask whatever you want. Well, I'll have a quick little set of slides that'll go through just some basic stuff on the exam. And then floor's open. You can ask whatever you want. And again, we're going to start a little early just to make sure everybody has time. There's a lot of back and forth in the manual and whatnot, and I don't want stuff like that to inhibit your exam. All right. Sound good? Everybody good on homework and whatnot? All right. Okay, so what we're going to do today is we're going to continue on our discussion with bolted connections, and we're actually going to get into some analysis today with a quick example. I want to go back a little bit to discuss like this right here. So last time we were looking at the two limit states associated with bearing type connections. So remember, really only one of two things can happen if we're talking about a connection that resists loads through pure bearing. Either the bolt's going to shear in half or we're going to fail the plate. Okay. Now to fail the plate, we have either tear out or ovalization, and that's where that whole 1.2 LC TFU comes into play. The big thing I want to make sure that everybody's clear on when we get into our analysis example today is that everybody's clear on the difference between what I'm calling an edge bolt and what I'm calling an interior bolt. So for instance, if I've got a plate, let's say I've got this table right here and I've got a bunch of bolts, right here, and I'm yanking on it. The edge bolts are the ones that are along the back of the connection. So for instance, if I've got my load, right here, and I'm yanking on the plate like so, these are going to be my edge bolts, and then my interior bolts are going to be that next row up. So everybody all right with that? If you can identify that, then I think a lot of the math will become basically just like grunt work, and it'll be very plug and chug. To calculate your LC distances, LC for edge bolts is just going to be your edge distance minus half a hole diameter. Then for your interior bolts, it's your spacing minus a full hole diameter. Okay? So that's really the only complication in bolt bearing computations. Your 1.2 LC TFU and your 2.4 DTFU. The LC is the only one that I think is going to trip you up. If you got that down pat, then everything else should run like clockwork. Remember, the upper expression is intended to ensure that the bolt or the plate around the bolt doesn't tear out, and then the lower expression is trying to prevent bolt hole ovalization, just get the hole literally stretching out and getting too long on you. Everybody okay with that? Okay. And again, one final point. We talked about this last time, but again, our hole diameters, when we look at bolt bearing capacity, our hole diameters are computed by taking the bolt diameter and adding a 1/16 of an inch, not an 1/8 of an inch. And I told you that would make you angry because we've been using an 1/8 of an inch this whole semester. But again, what we're looking at right now is not how much of that material contribute to the capacity of the member as a whole. We are literally looking at the physical capacity of the plate right there at the bolt. So we're using the physical dimensions, not that extra 1/16 of an inch. So it's the bolt diameter plus a 1/16. So everybody all right with that? And don't worry, I've got a nice little couple summary slides at the end that'll sort of bring everything together. All right. Sound good? All right. So today, before we get into our full-blown analysis example, I want to talk about how a connection should be laid out. I mean, I think design of a bolted connection and picking the number of bolts is pretty straightforward from a conceptual standpoint. I mean, if you got 100 kips on a connection and each bolt can hold up 20 kips, well, divide and you need 5 bolts. That's basically it, okay? But that's not enough. I mean, you have to actually lay out the bolts. You have to say, here's where bolt A goes, here's where bolt B goes, and et cetera. So what we need to discuss are the limits associated with how bolts can be spaced out, not only from each other, but from the edge of the plate, because that's going to matter when we start to lay out our connections. So let's take each of these one at a time. Now, if you want to follow along, I'm going off of Chapter J in the manual. So if you remember, we've already looked at some stuff in Chapter J before, because this is the stuff that we use when we were looking at threaded rods and threads excluded versus threads included, looking at those shear stresses. I don't have tabs for these particular sections because I'll be honest, I'm going to be referring to a bunch of different pages within Chapter J. So my advice would be, like, what I have is I have just a single tab just sort of placed at the beginning of J.3. So I'm on 16.1-118. I want everybody to make sure they're able to find that. And I just sort of have a tab placed here because I'm going to be going back and forth from page to page in the manual. So like this one's going to be on 16.1-122, and then I'm going to have one on 120 and 119. So I think it's easier just to have a general tab in this area. So everybody with me so far? Okay. So the first one I want to talk about is minimum bolt spacing. So if you go to 122, you'll find the section right here where it says, you know, item number 3, and it says minimum spacing. You read it out, and it says, so if we start going into the limit, it says, so the distance between centers of standard, oversized, or slotted holes shall not be less than 2 2/3 times the nominal diameter of the fastener, and a distance of 3 times the diameter is preferred. So, you know, if we're checking the, let's say we're checking the adequacy of a connection, so somebody provides us a design and we're checking it, I'm probably going to check based on ensuring that it at least meets the minimum requirement. But if I'm the designer and it's my job to actually lay out the connection, I'm probably just going to use 3 times the diameter. Now, here's just, it's a pretty simple limit to follow, but I want to make sure everybody understands why. So let me ask you a question. What do you think is the problem with bolts getting too close together? I mean, if I'm laying out a connection, what do you think is going to happen if the bolts get too close together? I mean, say it again. Exactly. You know, what happens if you've got a bolt here and a bolt here, and you start tightening in, they start clanking around on each other. You have to keep in mind, you have to be able to construct this connection. You have to be able to get a wrench around those bolts. So the bolts have to at least be some distance apart just to be able to put the thing together, right? So we have to have some minimum, at least some minimum limit on our spacing to ensure that we're able to facilitate construction. So a lot of these limits that we're going to be assessing are either going to try and meet one of 2 points, and one of them is facilitating construction. So that's what this one's for, to make sure that you can actually connect the beam to the column or the column to the brace, etc. Everybody good? So now that's one side of the coin. Here's the other side. Okay, so we also have limits on maximum bolt spacing. Now this one is a little trickier to understand, but everybody follow along with me. So, you know, we don't want the bolts to get too close together, because if they get too close together, they're going to start clanking around on each other when you try and connect the member. You're going to have a tough time getting a wrench around it. That's going to be a problem. Now what happens if they get too far apart? Well, let's go back to basics, all right? What are you trying to do with the connection? You're trying to take plate A and plate B and connect it together. Sandwich them together, right? So what happens if those bolts get too far apart is those plates don't really want to sandwich together, and you might have a little bit of a gap in between those plates. What do you think can get into that gap right there? Water, all right? And if water gets into that gap, what's going to happen? Well, you got water in contact with metal, and what does metal like to do when it's in contact with water? It likes to rust, yeah. So our 2 main reasons for a lot of these connection layout requirements are either A, to facilitate construction, to make the connection easy to put together, or we're trying to prevent corrosion, okay? So I want everybody to go to this, so this should be right around the same region if everybody's with me. We're on 16.1-124, and you should see these limits here for maximum bolt spacing requirements. So let me sort of go along on this with you. So I'm on the bottom right here under this table, what is it, J35M? Does everybody see that? Okay, good. All right, so read this out, and it says, okay, longitudinal spacing of fasteners between elements consisting of a plate and a shape or two plates in continuous contact should be as follows. If you notice, there's two limits, okay? One of those limits is associated with painted members, and one of them is associated with members that aren't painted, okay? And if you notice, if you read into it, so painted members spacing's either 24 times the thickness or 12 inches. For unpainted members, it's either 14 times the thickness or 7 inches. Now, you think about that, that kind of makes sense, because if you have a member that is painted, right? If it's painted, it has some protection against corrosion, right? And if it's got some protection against corrosion, we can get by with allowing a little bit more of a longitudinal spacing, right? But if it's unpainted, if it doesn't have any paint at all, well, then we've got to be a little more stringent on that maximum spacing, right? So we look at our connection, and we take the thinner part, and we say, well, it's either 14 times that thickness or 7 inches, okay? And that's going to be our maximum spacing. So check-in bolt layout requirements is pretty simple. Calculate a minimum spacing, calculate a maximum spacing. Hopefully our spacing is somewhere in the middle. Sound good? A very common bolt spacing used in fabrication of steel structures is 3 inches. 3 inches, more often than not, will meet your requirements for most commonly available bolt diameters. We'll check that, but usually if you space your connection out at, if you've got a bunch of bolts and you have a grid of bolts and you keep a 3-inch spacing, you're going to be good on spacing requirements. Now that's limits on how far apart bolts can be spaced from each other. We also have to talk about edge distance requirements. In other words, how far apart bolts can be from the edge of a given plate. So this is the only one that's a lookup. If you go to table J34, it's on 16.1-123, so it's literally back a page. This is what I was talking about when I was saying I don't place a tab on every single page in this chapter because I'm literally going back and forth. As long as you've got a single reference, I think you're going to be pretty good. So going to minimum edge distance, this is the only one that's a lookup. I mean, all the others you can compute a minimum spacing or maximum spacing. Yes, sir. Did it? Oh, no. Well, how many mistakes was it? Am I allowed 7 mistakes? Is that what it is? I'm only at 1. I think I'm doing pretty good, right? But then I'm the one who keeps track of the mistakes. Yeah, and what was it last semester? I kept having 4, right? Is that what it was? Yeah, you all let me know that. I remember that. Then you also made fun of my handwriting, so I haven't forgotten that. Oh. I'm going to remember that. All right, so barring my mistakes, everybody able to find this one? Yeah. On what was it? Maximum spacing. Okay. Is everybody able to find this one? Okay. All right. This is the only one that's a lookup. I would like it if there was a formula, and there is a general pattern to it, but by and large, this is one you've got to look up. This one comes from the fabricators, really, because there are multiple different means to fabricate a hole in a plate. I mean, you can drill it, you can sub-punch it, you can use a CNC machine or something like that. Depending upon the different fabrication techniques, honestly, fabricators get a little nervous when the holes get too close to the edge of the plate, because then they're worried about the plate distorting or they're not meeting the requirements of the drawing. So really the fabricator's like, you know what? In order for us to ensure that the connection meets the requirements that are set forth in the spec, these are our minimum edge distance requirements. So these just come straight from the fabricator. So those are the only ones that are a lookup. The edge distance requirements on the maximum end, the ones to prevent corrosion, those are simple. For edge distance requirements, they say, on the maximum end, let's just keep it simple. Either 12 times the thickness or 6 inches. And in terms of the thickness, on all of these, you're always going off of the minimum thickness. So if you got a 1/2-inch plate connected to a 3/4-inch plate, when you're checking minimum and maximum bolt spacing or edge distance requirements, you're going off of the thinner plate. So in that instance, we're talking about the 1/2 inch. All right? Everybody okay with that? Any questions so far? All right. So if you want this next slide, this is probably a good place to like put a big star or exclamation point or whatnot in your notes, because this is sort of a nice, hey, here it is summary on all of the calcs that we're doing. So last time we talked about bolt shear capacity and bolt bearing capacity. And if you recall, bolt shear capacity, that's a lookup. Okay? We don't have to do all the calculations. We go off of table 7.1. And that one should be tabbed in your manual if it isn't already done so. For bolt bearing capacity, that's one of the ones we sort of have to grunt out. 1.2 T times the ultimate tensile stress times the minimum of either our clear distance or 2 bolt diameters. Remember, don't forget phi. This is a very common mistake to forget, that once you've gone through and done all this, you have to adjust it by your safety factor. Okay? The only formulas that you need that aren't really explicitly stated here are these. Your clear distance for your interior bolts, edge bolts, as well as your hole diameter. Remember, 1/16 of an inch. And lastly, your relevant formulas for bolt spacing requirements. What I'm going to assume for most of the connections that we do in this course, I'm going to assume everything's unpainted. I'm going to assume the worst case scenario, which for most commercial steel structures, that's the case. I mean, most of your connections in a building like this, I mean, you go behind the wall right here and you've got a column and a beam framing into that. That steel, more often than not, was unpainted. So your maximum limit, I'm going to go off of 14T or 7 inches. But when we're in design mode, we're usually designing for minimum spacings, not maximums, because we want our connection region to really be as small as possible. Smaller connections mean smaller connection plates, which means less steel, which means less hit on the wallet of the client. Okay? Make sense? Everybody okay with that? All right. So I want to look at the following examples. So what I've got here is probably something akin to a splice connection. So I've sort of got member A, and let's say it's maybe member A and member B, and I want to splice them together. So what I might do is I might put a plate back here and a plate in front and sort of sandwich them in and bolt them together. Everybody okay with that? So I have a 3/4 inch, I'll call it the center plate or the main plate, and it's being connected to 1/2 inch thick plates on the top and bottom. And I have bolts going through. So help me out. We in single shear or double shear? Double shear. There we go. All right, so we got a double shear connection. We've got 6 bolts. Now, you're really going to want to pay attention to your spacings, because if you look, one of my edge distances is going to be 2 inches, but another one is going to be 2.5. So this just becomes a bookkeeping issue, making sure you're clear on that. Okay, so we've got A36 steel. We have 1 inch diameter Group A bolts, Group A X bolts, so that means that the threads are excluded from the shear plane. So we're going to determine the capacity of this section. We're also going to determine if it meets layout requirements. Now, before we start checking this out, let's also be clear, this is still a tension member, okay? We're still taking a piece of steel and yanking on it, okay? So there's still gross section yielding, net section fracture, block shear, all that stuff still matters, okay? We're just not going to worry about it on this example because we've already done that. I mean, you all got homework on that right now, sort of, you know, beat a dead horse with that. Bless you. All right. So everybody all right with that? Okay. So let's just sort of get into it, and let's take it one step at a time. All right. So let's see. So, all right. Example 8. All right. So let's right off the bat, let's just list some properties regarding this connection that are going to be constant throughout the entire calculation. So let's start off with something simple. Let's start off with the bolt holes. Let's see if everybody's awake. All right, so bolt holes. Now, help me out. What's the diameter of the bolt? 1 inch. So what does that mean? 1 1/16. There we go. So the hole diameter is 1 1/16 of an inch. Or if you want a decimal value, what's that going to be? Oh, I'm making you break out the calculator. Oh, no. Now, we're going to work on this one together. Say it again. 1.0675? We got 2.5. There we go. I'm gonna actually write the whole thing out because, you know, with bolted connections, I actually want the connections or the calculations for a single bolt to be somewhat precise because we're going to take that and then multiply it by the number of bolts. And some of these connections we might have 30 or 40 bolts or something. So I'm going to try and be a little precise with that. Okay, now that's the bolt holes. Now let's also look at the steel. So we've got, what was it, A36? A36 steel. So help me out. If we got A36 steel, what is our tensile stress? There we go. Going to the table 2-4. 58. Remember, when you got the range, go off the minimum. So we'll say FU is 58 KSI. And I'm going to go ahead and say, all right, we've got table 2-4. All right? Sound good? So that's just me sort of referencing where I'm getting that from the manual. All right. Everybody good? Now, we got two different limit states that we're going to assess. All right? We're going to look at bolt shear and we're going to look at bolt bearing. So let's do bolt shear first. Okay? So let me go ahead and write that out. So bolt shear. Bolt shear. All right. Now, remember, we sort of got our handy-dandy little A in the middle of the manual, right? So we're going to 7-1. Remember this one, available shear strength bolts. Okay, now remember, which numbers are we looking at? Green numbers or blue numbers? Blue numbers. There we go. LRFD. All right, so tell me what I need to know in order to properly look up values for this connection. So what type of bolts do we have? Group A, Group B? There we go. All right, Group A. And then that's included or excluded. Okay. Now we said the diameter of the bolt up here was 1 inch. And then you all answered this earlier. Which shear were we in? There we go. Okay. Now, based off of these parameters right here, I want you to tell me the following. What is the shear capacity of a single bolt? 80.1. Does everybody see that? Okay, so 80.1. And what I usually do is I say that's phi RN, but I use a little r to say that's just, you know, per bolt. So phi RN is 80.1 kips per bolt. Okay, so just on magnitude, that's 80,000 pounds to fail and shear a single bolt. But again, we're talking about a bolt that's, you know, yay thick, and we're not going through the threads, and it's in double shear. So yeah, it's going to take a lot of force to rip that bolt in half. Now, remind me, how many bolts do we have in the connection? 6. All right, so therefore, we wanted to do capital phi RN, you know, phi RN for the whole connection. We're just going to literally take, here's the capacity of a bolt. There's 6 bolts in the connection. It's that simple. So we just say 6 bolts times 80.1 kips per bolt, and it's that simple. So what is phi RN? 480.6. See, that's not so bad, is it? Yes, sir.
So that would be the available shear strength of
Yes.
when you are loading that connection, are they all seeing equal amounts of force, or do they each see a different amount based on the pattern?
That's a great question. And the answer to that question, you know, are they all seeing the exact same number of force? The answer is no. They actually aren't. There is going to be variability between how much bolt A sees versus how much bolt B sees. So to answer your question, yeah, the bolts are going to see different stresses. Now, how do we handle that? We're sort of handling that in the background. Okay, when you go to the manual and you look up the nominal shear stress of a Group AX bolt, and it tells you it's 68 KSI, there was a lot of stuff that went into the background to develop that value of 68 KSI, and one of them was to count for reduction in capacity due to connection efficiency. In other words, some bolts are just going to see more load than others. Okay, now I will say this. for connections like this, we're sort of putting the blinders on and just saying, you know what, we're just going to assume that they're all equally loaded. Okay? But if you have what's called an eccentrically loaded connection, so let's say you've got, I don't know, maybe like a column, something like that, and you have, you know, maybe some element framing into it, and then you have, you know, a number of bolts right here. But instead of yanking on it like this, you know, yanking on it in pure shear, if you're doing this and bending it, then it's a whole different story, because in this instance, I mean, think, you know, sigma equals my over I, you know, this bolt is going to be experiencing a different stress than this one. And we can explicitly go through and compute that, and we do that, you know, later on when we start tackling some more advanced topics. But if you've got a connection that's just being yanked on, yeah, the bolts are probably going to be experiencing a little bit of different stress here and there, but that math is sort of handled a little bit in the background. For what we're doing, we can just say, you know, 80 kips per bolt times 6 is good enough for what we're doing here. But that's a great point to bring up. Anybody else? This is good stuff. Anybody else? All right. Yeah, please, if you got anything, I mean, this is good stuff. All right. So this is bolt shear. Okay, let's look at bolt bearing. Now, you're going to be mad at me, but this is just how we have to do this. Unfortunately, bolt bearing calcs can be a little bit repetitive, and I'll explain why. Okay, so let me go back to the PowerPoint just to bring up the image a little bit. Okay, so here's the image associated with our connection. I want to make 2 points. Okay, when we do bolt bearing calcs, we always have to look at, you know, at least 2 different situations. I mean, what are you doing in a connection? You're taking member A and you're connecting it to member B. Okay, and when we're doing bolt bearing calculations, we are evaluating not the bolts, we are evaluating members. So at the very least, theoretically, we have to do at least 2 bolt bearing checks. One for, in this case, plates transferring load to the left, and then another one for plates transferring load to the right. Make sense? Now, sometimes we can be a little crafty and use a little bit of common sense. For instance, if we just had a single lap connection, so we just had plate A connected to plate B, and they both had the same dimensions, the same steel grade, and what have you, well, we don't really technically need to do 2 checks. We can just do 1 because they're both the same, right? That's not the case here, okay? If we look at the plates transferring load, let's say to the right, we've got 3/4 inches of steel, right? But the plates transferring load to the left, we 1 inch, right? Because we got a 1/2 inch here and a 1/2 inch here, right? So we have a greater thickness of steel transmitting load in this direction, all right? That makes sense? But if that was the only variable, maybe I could say, oh, well, we just need to check this one, and that's fine. Because less steel, this is going to be the weaker plate. This is going to be the one that governs. But this plate has a longer edge distance here. This one has 2.5. This one only has 2. So which one governs? The thicker plate with the smaller edge distance, or the thinner plate with the larger edge distance? Well, I don't know. That's why we have to do both. Okay. Plus, what if I made it even more complicated? What if I said this one is A992 steel and these two are A36? Now you got different steel grades in the mix, and now it becomes even more difficult to predict. And the only way to handle it is to just roll up your sleeves and do both. Okay. Now I think you're going to find a pretty clear result when we start going into this, but you know, it just sort of it is what it is. All right. Everybody okay with that point so far? Everybody good? All right. Now, okay, so let's take care of that center plate. Okay, let's take care of that one. Okay, center plate. All right, so we're going to need a few quantities to sort of check this out. But before I do that, let me go ahead and draw out just sort of an image of what that center plate looks like. Let me bring up the image real quick. Okay, so I'm looking at this 3/4 inch plate, the one in the middle, and trying to draw it to scale. It probably looks something about like this. So We've got a plate going like that. There's my brake line. And then I'm yanking on the plate, and something like this. Okay? And I've got 1, 2, 3, 4, 5, 6. Okay? All right. So this is just looking at that center plate. So these center-to-center spacings of the bolt, these are the what? The 3 inches? Okay, all right, 3 inches. All right. So that means this one's 3 inches. This one's 3 inches. Sound good? And our edge distance, the one on this back end, that's the what? That one's 2.5, right? Again, looking at the center plate, it's the 2.5. For the cover plates, it's the 2 inches. Everybody okay with that? All right, so this is, I'll just say 2.5 inches. Like that. Sound good? All right. So let's start writing this out. So we have an S value. We have an S value of 3 inches. We have an edge distance of, what is that, 2.5 inches? And we have a thickness of 3/4. So far, so good? All right. Now, in order to do a bolt bearing computation, okay, we're going to need a clear edge distance or a clear distance between the bolts for the edge bolts and for the interior bolts. So we're going to need an LCE and an LCI. So let's just take these one at a time. How do I compute LCE? I'm making you go through your notes. Oh, no. There you go. So does everybody see that? It's the edge distance minus half the hole diameter. So L sub E minus DH over 2. Sound good? All right, so let's just sort of check that out. So the edge distance, that's 2.5 inches minus 1/2 of the hole diameter, which we went and did that up here, and we got, what was it, like 1.0625? All right. So tell me what you get here, and we'll just say 3 decimal places. That's fine. 1.438. Anybody second that? Oh. Oh. You got voted down. 1.969. Was it the half? Ah, that's no big deal. No biggie. All right. LCI. Now, what's LCI? Oh, it's right there. There we go. You do know. I challenge that, sir. S minus DH. All right, so that is 3 inches minus 1.0625. Okay, so what's that going to be? 1.938. I got a second on that? All right, there we go. All right. Okay, now, yes, sir?
How do you address spacing?
You mean like if you've got a staggered connection?
If it was like 2 inches in between the first bolts, do you ever...
Yeah, honestly, you'd have to just take each bolt one at a time, like literally look at this one and say, okay, what's the edge distance? Look at this one and say, what's the edge distance? I'll say this. In most cases, a fabricator isn't going to want to do that, nor is an engineer going to want to do that, because all that's going to do is just make it complicated, and us engineers, we do our best to try and keep it simple, so that more often than not wouldn't happen. Now, what really could happen is a staggered connection. So if you've got that sort of checkerboard type pattern, and you just have to be diligent in your bookkeeping. You know, look at the edge distance on this one, the edge distance on this one, and et cetera. I won't do that on an exam just because it doesn't become hard. It just becomes more bookkeeping, and then it's not really a test of the materials. I won't do that on an exam. I might do it on a homework, you know.
When you're measuring on a stagger pattern, do you go between just like this one, this set of bolts, and then just the next set of bolts, or then matching?
The best way to answer that is because, you know, staggered connections can be laid out in any different pattern. You measure along the line of where the load's being applied. So we are measuring edge distances essentially this way because, like, if we're looking at, let's say, an interior bolt. So here's our interior bolt. The center spacing is 3 inches, but the clear spacing is 3 inches, half a hole diameter, half a hole diameter. But that distance, we're measuring it this way because, think, if I'm yanking on this, right, or actually, I have to be over here. If I'm yanking on this, right, we're doing these calculations to account for bolt tear out, right? And think about what would happen. We're essentially talking about the plate sort of ripping out like this. So the distances that we're measuring along the plate. Because what we're trying to prevent when we look at these calcs, we're trying to prevent like a little crack happening right here and here, and then this sort of region of the plate just sort of prying out. You see what I mean? So always just measure along the plate. So if you got a staggered connection, that's really just the easiest way to think. As long as you're going that way, you're good. Is that everybody else all right with that? This is good stuff, okay? All right. Okay. Now, I have one more value I want to compute. So if you all are looking right there at that slide, you should see that we've got the bearing capacity of a plate, and we're comparing these clear distances to what? We're taking the minimum of this and what? It's the minimum of LC and something, making you all, there we go, 2 times the bolt diameter. So let's just go ahead and write here and just write that down. So what's 2 times the bolt diameter? Well, what's the bolt diameter? There you go, 1 inch. So 2 dB is 2 inches, all right? So I like to go ahead and just sort of put this right here because let me explain how this is going to work. So we're going to compute a bolt bearing capacity for an edge bolt, and then we're going to compute a bolt bearing capacity for an interior bolt. So you tell me, for each one of those, are we going to use this, the 2 bolt diameters, or are we going to use these, the clear edge distances? The clear distances, right? Because we calculate and it's either the minimum of these or that. And in both cases, these are smaller than 2 dB, so we'll just use those. So let me explain. So I'll show you how this is going to work. All right, before I go, has everybody got all this? Everybody got all this? All right. Whoop. All right. Okay. So here's how we'll do this. I'm going to calculate a nominal capacity of an edge bolt. And I'm going to say it's 1.2 T FU times the minimum of LCE, or 2 bolt diameters. But I don't need to do that evaluation at the end because I've already done that. It's going to be LCE. So let's plug and chug. You tell me. So it's 1.2 times, now what's the thickness? 3/4. Again, we're looking at the center plate, so 3/4. All right. FU, what was that? Or we looked that up way back. 58. And what do we do here? No. Between LCE and 2 bolt diameters, yeah. So, well, no, okay, so I'm looking, that's a good question. So I'm looking at an edge bolt now. I'm going to take this and do it again and have an RNI, a capacity for the interior bolt. So now it's just the edge bolt and a 2 bolt diameter. So what was this one? That's a good question. I'm doing that, okay, that's sort of my way of recognizing that I'm only looking at a single bolt and not the entire connection. Remember what I did back here? See this right there, how I had phi RN, but I had a little r to say that this was 80 kips per bolt, and then this was the capacity for the entire connection. It's just sort of the same notation. Remember, I'm just looking at the capacity of one edge bolt, okay? So that's why I use a little r. Everybody okay with that? That's just sort of my way of keeping track of what's going on. All right, so what was my LC value? I don't remember if I got that. There we go, 1.969. All right, so whoop, I can do better than that. You tell me, what do we get here? 102.78. Do I got a second on that? All right. Now, 2 points I want to make. So again, that is the capacity for just a single bolt, but one thing we have not done yet is we have not applied phi. We have not applied our resistance factor. Don't forget to do that at the very end. All right? So that's Rn for an edge bolt. Rn for an interior bolt is 1.2 TFU times the minimum of LCI, or 2 bolt diameter. So this is where your question, Mr. Hampton, comes in. That's where the interior bolt comes in. So all right, so same story. So 1.2 times 3/4 of an inch times 58 KSI times, what's our value going to be here? 1.938. All right, so what do we got? Oh, goodness. 101.16. So I got a second on that? All right. All right. Okay, now I'm going to need your help. So this is the capacity for an edge bolt, and here's the capacity for an interior bolt. So you tell me, what do I need to do to get the capacity of the whole connection? Well, how many? Okay, so how many interior bolts are there? 4. And how many edge bolts are there? 2. All right. So 2 times the capacity for the edge bolt, 4 times the capacity for the interior bolt. Add those up. That'll give me the capacity for the whole connection. So here's my big Rn. So Rn is going to be 2 RNE plus 4 RNI. So 2 102.78 plus 4 101.16. What do we got? So 610. We'll cut it down a little bit now. We'll say 610.2. Now, do I have a second on that? All right. What did I forget? There you go. Now, what is phi? 0.75. There we go. So therefore, phi Rn is 0.75 times 610.2. So we'll just put that over here. So phi Rn comes out to be what? 457.7, is that what you said? All right, do I have a second on that? There we go. Now, let me ask you this. Based off of what we've done so far, if I start loading this connection, does bolt shear govern? Think about that. Think about that. No, right? Because look at the capacities. The capacity in bolt shear is about 480 kips. But for bolt bearings, so far, our capacity is 457. So what that means is if I take this plate and I start yanking on it, the plate is going to fail before the bolts snap in half, right? So this is what governs the capacity of this section so far, okay? We're technically not done because there's a whole nother set of plates we got to assess, okay? Now here's how I'm going to handle that, all right? So I'm going to make you all do a little bit of work. Oh, no. So we're going to look at case 2. We're going to look at the cover plates. Now here's the easiest way to handle this. All right. Number 1, all right. When we did the main plate, we started listing some parameters like what's the bolt spacing, what's the thickness, what's all that. So let's just sort of keep that same pattern. So for cover plates, what's the bolt spacing? 3 inches, that and simple. All right, now, here's the kicker. What is the edge distance? This is one point I want to make right now. What's the edge distance? 2 inches. For the cover plates, it's 2 inches. Okay? Now, that's the first point I want to make. Here's the second point I want to make. Now, the thickness. Okay? There's 2 ways of going about this. Okay? One way is we could say that the thickness is 1/2. Okay? Compute the capacity, and then at the very end, multiply by 2. That's one way of doing it. The other way of doing it, which is what I think is the easiest way, is to just say the thickness is 1 inch. I think it's a lot easier to do that now because when you're down the line and you've already done one of these and you get into that repetitive, well, it's still 2 edge bolts, it's still 4 interior bolts, so now there's phi. It's very easy to forget to do that. So right off the bat, I'd say, you know what, let's just take care of that now and don't worry about it. Let me just say this. You can do either one and you will get the same answer. I just think it's easier to get that out of the way now. Yes, sir. That's a little rare. I'd say you probably wouldn't do that. What you can get are fill plates. Okay. Now, what I mean by a fill plate is, let's say, let me see what time it is. Okay. So let's say you're trying to splice member A and member B together. Okay. And let's say you're trying to splice together some I-beams, some really big I-beams. Well, what might happen is you have, I-beam over here. So here's the flange. And there's the flange, right? And then you want to splice that to another member, but let's say it's bigger, okay? Let's say it's like this. So it's a deeper section, okay? So how do you splice them? Well, I might say, all right, let's put a plate, up top and a plate on the bottom. But there's a problem, right? There's a little gap, right? So a lot of times what fabricators will do is insert what's called a fill plate to fill up that little gap. So it might be, something like 1/8 of an inch or what have you. It's not a structural plate and it's not resisting any load. It's just there to get an even surface to splice member A and member B together. So that can happen. But different size splice plates, more often than not, no, you're not going to do that. Does that sort of answer your question? Did you have a question? Well, what I'm getting at is, okay, think about this. When I yank on this, okay, think about how the load's being transferred. Okay, when I yank on this, I've got a load on this member. That load is going to these bolts, so it's going into this plate. And then that plate, the bolts are ultimately going down here. I mean, yeah, you can develop some friction forces here and there. And when we do slip critical connections, we do have factors where we have to consider how many filler plates we have. But by and large, they're not structural like the cover plates are. I mean, those cover plates, they're the ones who are really taking on the large majority of the work that's being done. Now, let me also say this, you can have multiple filler plates. Like if you've got a really odd, like if you're trying to do 3/16 of an inch, you might put something like 1/4 of an inch or 1/8 of an inch and then another 1/16. So you might have multiple filler plates in there, but mostly friction is really what they're going to be seeing, and that's about it. This is good stuff. Anybody have any other questions? This is really good. All right. So I'm just curious. I'm going to let you all sort of toy around with this on your own. But this calculation, let me be clear, is the exact same as what we did before. We have the same bolts. We have the same ultimate tensile stress. The only thing that's different is we now have a different thickness and a different edge distance. So unfortunately, all that stuff that we just did, the RNE, the RNI, the RN, the PRN, you just got to do it again. So I'm curious, you tell me which one's going to govern. So we'll come back to this on Monday. I want to sort of revisit this connection and see which one's going to govern. One thing I will say is after we get into that, we're going to get into design. And I'm just going to say design, it's pretty simple, okay? What I said before, that's basically it in a nutshell. You literally take the factored load, 1.2 dead plus 1.6 live, you got the load. You take the capacity of a bolt, all right? So if I have 100 kips on that connection and each bolt can hold up 10 kips, how many bolts do I need? 10 bolts. 10 bolts, use my bolt spacing requirements to figure out how to lay them out. Check bolt bearing, that's it. There's nothing else to it. If bolt bearing fails, maybe take your bolts and space them out a little further. That's it. There's really nothing else to it for bolted connections. We'll have a quick example on that, and then we'll get into our sort of second class of connections, which are slip critical connections. Those are where installation methods, friction, and things like that come into play. Sound good? All right. For those of you who are not in concrete design, you all have a great weekend. We'll see you when we get back. And those of you who are in concrete design, I'll see you in about 10 minutes. All right, we'll see you.